Okay. Hey, everybody. I am Dr. Eberly. Welcome to Chemistry 1402. It is dark outside right now because that's when my children sleep, and that's when the best time for me to record this was going to be. So a couple of things about me before we just jump into everything. One, I'm looking forward to getting to know you guys as best as I can in an online chemistry class. There will be a few labs we have face-to-face, so we'll get to meet then. And that's the probably the main thing I miss most about not having our lectures be face-to-face is getting to see my students, getting to know my students, but we're still going to do that as best we can in an online chemistry class. So other things about me. Excited for this course. I'm excited to have you in this course, but I have a wonderful family, my husband, and we have 2 kids. And I think I mentioned in my email, we have a 2-year-old. She's almost 2.5. Her name's Finley. She's awesome. She's crazy. She's just full blast is really probably a better word for that. During quarantine, she's just been literally running around our house. And we have a 7-month-old son named Joel. He's pretty awesome too. He's finally learning to sleep through the night pretty well. So I'm thankful for that. Things I enjoy hiking. You guys are going to learn more about that as the semester goes. We enjoy hiking, like to get outside. I enjoy cooking, exercising, all things coffee. Enjoy that. A couple things about this course, just to give you, make you feel kind of at home or as best I can and make you feel welcome in it, is here is probably the most controversial part of this course. Some people feel, there's going to be students that feel like we are moving at a decent pace, and they're fine with that. You're hanging with it, you feel on top of things, and then there's going to be other students who feel like we're moving really fast. And that's because some of you may be well-versed in chemistry, some of you may not be well-versed in chemistry at all, and that's okay. We're all in this together. The main thing I want to encourage you with is to reach out for help. Okay, I am here to help you, so take advantage of that. And I'm also going to provide free tutoring resources from our department, from the university, and I want to encourage you to take advantage of those anytime you need them. Please, I'm a kind person. You can email me your questions. We can set up an individual Zoom meeting. I had a lot of students in the fall do that. We would meet on Zoom for 20 minutes or so. They'd ask me their questions. We'd walk through things. We'd work problems from the homeworks or from exams. After you take exams, if you want to look at anything, I'm here to help. Okay, if there's ever a concept that you feel like I moved through too fast and you still have some questions about it, shoot me an email. The biggest thing is don't wait. Don't just let those questions build up and then the night before the exam, I'm not available to help you. Please reach out and allow me to help as you have questions. And then another way I want to help kind of create some community in our class and help you guys is we'll create a course in GroupMe. I'll get that information up and going within the first week or 2 of class. And that was a lot of students really said that was helpful this past fall as well. So, and I'm open to other ideas. If there's other ways that you guys know of or think of, things that are helpful from another course that you see happening, please bring those ideas to the table here in this chemistry course so that we can all benefit from those as well. Next, we're going to look at a few things from the syllabus. So I'm going to share my screen here in a second, and then after the syllabus, I'll go ahead and jump right into lecture. We'll be going over matter and chemistry slides, so have those slides available to look at. I organize these slides as a fill-in-the-blank style. That's to help you engage, okay? So I used to not do fill-in-the-blank when we were person or face-to-face, but I found that that's more helpful for the online stuff. So be careful to, do those as you go, take extra notes, and once we're done, that will conclude this first lecture. So I'm going to share my screen now. Okay. You should be able to see my screen, and what you should see is the syllabus, the course syllabus. This is on Blackboard, in our Blackboard course, so hopefully you've taken a minute to look over it. I know it's like 7 pages long, so that might sound pretty daunting, but please please take time to read over the syllabus in detail. It contains so much helpful information that you need to know about this course, how I handle exams, quizzes, homeworks, lab assignments. I'm just going to give you kind of a helicopter ride over this, so I'm not going to get down in the weeds of everything, but just know I've tried to work really hard to make all this information easy and organized for you. First off is just the basic information about me. Office hours, I think, are an important thing to know is that I'm going to have office hours every Tuesday, Thursday at 9:30 to 10:30 on Zoom, as well as Friday, and here are the links for those. No passcode required, the way a passcode is required for lecture. You can just jump on and ask me your questions. If these times don't work for you, shoot me an email and we can set up an individual Zoom meeting. And then we have the 8 a.m. lecture, the 10:50 lecture, and all the lab times. Some of you will be in a lab section with Dr. Dunlap. She is amazing. So you're in great hands there. Nothing will be very different. We're going to be doing the same labs and everything. It's just that some of you will be with her for that lab period. Course materials, the only thing that I am requiring is that you have to have some form of the textbook. Electronic version is acceptable, but you need to have modified Mastering Chemistry access to that. That's how you're going to do all your homework assignments for this course. If you get that, it comes with access to the electronic text, so you don't need a hard copy. Some of you may like to have a hard copy, that's fine as well. Please read through the other things I want you to have for this class course, or a calculator. Skip over the prerequisites and objectives. Weekly assignments, this kind of gives you a rundown of what we're going to have every week. Lecture, you are pretty much going to have a quiz almost every single week. I have textbook reading that I think is essential. Obviously, it's not mandatory, but I'm really asking you to take that seriously. It's going to help you. Students that have done it really said it's helped them as they go. Also, it's quick reading. It's not like a whole chapter for every lecture. It's a couple of sections. So please do that before you come to the lecture if you can. The homework assignments, the labs, there's a lot of info here with the labs. Mainly you need to see Blackboard to determine if you're in lab group A or B, because when I show in a minute on the schedule, there's going to be certain weeks where we split up into groups, mainly because of social distancing. Our labs have a certain capacity. And so we've had to break things down into group A and group B. So make sure you know which group you're in so that when you look at the schedule, you know when to come to lab or when to not for our 3 face-to-face labs that we'll be doing this semester. I'm going to post some supplemental videos. These were very helpful to students. I may work a homework problem. I may work a problem from one of the dry labs and teach you how to do things. Those are helpful on the side. I'll post those to Blackboard. And then I'll have extra review sessions. Sometimes we'll use lab time for reviews if it's right before an exam. Sometimes there may be extra sessions outside of those. Here's the kind of the grading rubric per se, how it all comes out, points. I will keep Blackboard updated with your grades. So if you're wondering what grade you have in the course, you can always check Blackboard for that. If you ever have questions, you can let me know. Now at the end of the semester, I'll have to do maybe some manual calculations to get your final grades, but everything should be up to date on Blackboard. Here's what's important: missed exams and quizzes. So I allow you to essentially drop one exam, but your homework score will replace an exam. So it's not that you just get to drop one, but let's say you have to miss an exam for whatever reason. I allow your total homework percentage to replace an exam score if your homework percentage is higher. So you're going to have 10 10-point homeworks across the semester. So that adds up to 100 points, and that can replace one exam, one 100-point exam. All right, and that is right here in red, okay, this policy. So just know you essentially kind of get to drop one if for some reason something comes up and you have to miss an exam. Therefore, let me continue reading. Therefore, a missed exam, additionally a missed quiz will not be made up. Quizzes, if they're missed, but if they're late, my policy there is you get about half credit. Any late work, labs, quiz, I know things come up, so please don't make a habit of turning things in late. I will notice if it's habitual, but I understand if something is turned in late. Now, homeworks, With mastering, I can't go back in and edit things. If you have a valid reason, send me an email. I can work with you. But so I have a little bit of wiggle room for late work, but please make every effort to get things done on time. I give you a heads up. You usually have plenty of time to do things. So please don't be late on stuff. Also, I want to say this. Let me go back up to this paragraph right above. In fact, I'm going to turn this sideways. Maybe you can read it better. Okay, exams. All exams will be online at Blackboard. You're not going to be using Respondus lockdown browser stuff in my course, which essentially means exams will be open note, open book. However, you will be signing an academic integrity policy for every exam and quiz. And then I want to read the part in blue. This is the non-fun stuff. Please know any confirmed case of cheating or academic integrity violation will go on your permanent record. And unfortunately, I've had several of these this past fall. It was not great. Please, this course, I want you to learn, and I want these exams to be a test of how much you've learned from this course. So I hope you take that seriously, even though you're going to have full access to your notes and your book for those exams. Attendance policy, I mentioned this in the email, but please have your videos on for that. It's going to help everybody out. I've already gotten a thank you email that I'm asking students to do this, because I think it's hopefully going to be helpful. All right, I'm going to scroll on down. There's a bunch of policy stuff from the university. Turn my screen back. Okay, here's our lecture schedule. Again, if you've seen this, great. You can skip over the syllabus stuff and go on into the lecture slides. But if you haven't seen this, if you're looking at this for the first time, this tells you what chapter we're covering every week, when your exams are, and it tells you when your assignments are due, okay? Assignments due are in red, and then it tells you what the assigned reading for that week or for that lecture is as well in the final column over here on the right. So this just tells you heads up whenever there's no surprises. Usually not any surprises, I should say. Here's our laboratory schedule. So it tells you what labs we're doing every week, when they're due. So no guesswork there as well. And then if you're ever needing, here's all of our Zoom links for the labs as well. This is how you'll get on every single week. So you don't have to, don't worry about misplacing this. They'll always be on the syllabus, which is always on Blackboard. And you'll just jump on the Zooms for labs when we're not meeting on campus for a lab. And I do want you to show up to the labs. Those are mandatory as well. And they're more beneficial because you'll get to do them with classmates. You'll build relationships with your classmates. It'll be way easier than doing the labs on your own. So you do need to show up to the labs, even though they're online as well. All right, let's go ahead and jump into the lecture material. That's really all I wanted to cover with, I need to scroll up. It's really all I wanted to cover on the syllabus. Grab a drink of water. Okay, so Matter in Chemistry is the title of these slides. Chemistry for Health Professionals, which is going to be you guys. I love to start out the semester with a quote. I love this quote because here's the deal. I know chemistry, that word kind of evokes different emotions for different peoples. For some of you, you're excited about it. For some of you, you're very nervous. You're very worried about this course. You think it's going to be the hardest course you have all semester. But here's what I want to challenge all of us to do, including me. So I'm just going to read this quote. It says, "It's been my experience that you can nearly always enjoy things if you make up your mind firmly that you will." I'm going to circle two words here: enjoy and firmly. Is it bad of me that I want you guys to not just get through this course, but I also want you to enjoy it? I think that's possible, and I hope you think it's possible too. Some days enjoying it might be a little easier than others, okay? That's why I think the second word is important, firmly. I'm asking you, I'm going to make up my mind firmly that I'm going to enjoy this course with you. I'm going to do my best to help you and champion each of you. And I'm asking that you will make up your mind firmly to give me your best and enjoy it if you can. I told you that I enjoy hiking. I want you to get the full picture here, so I'm going to turn my slides back. I always like to start out my lectures with a picture of a hike that I've either gone on recently or gone on in the past. So this is me and my husband at Hawksbill Crag. Maybe you've heard of this. This is up near the Buffalo River Outdoor Center area. It's also known as Whitaker Point. It's maybe one of the most iconic hikes in all of Arkansas. You have this big rock jutting out over into the nothingness. So they call it the crag. And people love to go take pictures here. There's no rails, obviously, so be careful if you go. It is a dog-friendly hike. I've had people ask me, you can take your dog or pet, just make sure you have them on a leash and just be very careful. But a beautiful hike. It's not incredibly strenuous, but one you should definitely go on if you've never been to it before. Now, I'm not just going to show you pictures of hikes all day long. This one actually has a purpose, but this is the Grand Canyon. We got to go here for our 1-year anniversary, and there is a trail that we got to hike. I'm going to outline it in red right here. It's called Bright Angel Trail, and it goes all the way down to Plateau Point, which is right here. I just circled it, and it's in the middle of the canyon. It's amazing because when you're standing on Plateau Point, you're just like totally engulfed in the canyon. You can look up, there's canyon, you can look down, you can see the Colorado River. It's beautiful, but it is not for the faint of heart. It's a pretty intense trail. But when you look at this picture, what do you see? So we're actually going to start talking about chemistry. You see stuff, right? You see the sky, you see different layers of earth, you see different colors. I think that's an amazing part of the canyon, the different colors of earth and the different layers. You see trees, you see all kinds of stuff. And this is what chemistry is about. It's about studying stuff. It's a very vague definition, I know, but it's about studying. Another word, fancy chemistry word for stuff is matter, okay? So what is matter? We already said matter is stuff, any kind of stuff. But if we're going to actually put some parameters on this, matter is anything that has mass and volume. And, you know, I just remembered that red may be kind of hard to see. So I'm going to switch over to black for some of this, unless I'm on white. Hopefully you can read that. Matter stuff is anything that has mass and volume. So I've got a picture here of one of my favorite forms of matter. It's a cheeseburger. I used to make people tell me their favorite place to get a cheeseburger, but I won't be able to hear any of you respond because it's a recording. So you can email me your favorite place to get a cheeseburger. My favorite is in Little Rock. It's a place called Big Orange. If you haven't been there, it's really great. So here's an example of matter. But I want to expand your mind for a second. I want to ask you what is, and this is a decent size, right? But I don't know if black is going to show up very good. What would be, if we were thinking of a range of matter, what would be the smallest kind of matter we could think of? And then on the other side over here, what would be the largest kind of matter we could think of? I want you to think for a second. Let's first start with the smallest. The smallest kind of matter. And remember, matter is anything with mass and volume. What will be the smallest? Some of you may be thinking like a piece of dirt. It gets much smaller. Some of you may think like a bacteria. That's pretty small. We can get smaller though. A virus can get smaller than that. Some of you may have already said it or thought it or wrote it. An atom is pretty small, but we can actually go smaller than the atom. The smallest thing, if we're being super technical, is called a quark. Q-U-A-R-K. This is a subatomic particle. So it's a particle within an atom, okay? But an atom would be a pretty good guess. If you guessed atom, good job. So a quark, okay? This is even smaller than, say, an electron, proton, or neutron. Those are also subatomic particles, but the smallest here is a quark, similar to an electron. On the other hand, what would be the largest kind of matter that you could think of? Very, very big now. We're going huge. We actually have to leave our planet if we're going to think of the largest kind of matter. It's a star. Anybody ever heard of the largest star in our universe? It's called Canis Majoris. I think I spelled that right. It might be IS. Canis Majoris. And this star is insanely large. I used to have a picture, but like if this is the star Canis Majoris, our sun, you'd have to like really zoom in. I probably can't even make a dot that's small enough. Our sun would be like the size of that dot. That would be our sun. Okay. So that's the largest type of matter, something that has mass and volume. So chemistry, though, is the study of matter. And how do we study matter? Well, there's different ways you can study properties of matter. Some examples of that. You can think of any examples of different properties. Well, size. You can measure the size of matter. Color as well. We can study color, how color changes. Temperature. We can measure temperature. I'm going to abbreviate. Okay, these are all different properties we can examine, observe. Some other examples that I didn't leave space for: density is a property that we can observe or measure. Reactivity is another one. Okay, so we will do that this semester. We'll be familiar with that. Size encompasses like length and volume, mass as well. Besides just looking at properties of matter, we also look at how matter changes, okay? So there's two major ways that matter changes. The first way is there are physical, matter can undergo a physical change or a chemical change, all right? Now, a physical change is one that does not alter the chemical makeup of that matter, but a chemical change does alter the chemical makeup of that matter. So I've got some pictures down here. One of the main things I want you to take away from this lecture today, we are going to identify 4 signs of a chemical change, okay? 4 signs. So some of these pictures are going to start introducing to us signs of a chemical change, and we're also going to look at physical changes. So let's look at this first picture. Now you see a beaker. What else do you see? I want to ask you, do you think this is a physical or a chemical change? Okay. Well, I see a flame. Okay. You see different colors here. If you guess chemical, you are correct. Okay, this is a chemical change. And how do we know that this is a chemical change? When you see fire, that's usually a good indication it's a physical change, okay? But I'm not just going to write fire here. What's happening is a fire is kind of a sign that there's a temperature change, okay? Fires heat things up. So obviously, if there's a temperature change occurring in this beaker, evidenced by a flame, so it's the fact of a temperature change. That's the first sign of a chemical change, okay? So we know it's chemical because there is a temperature change. So I'm actually going to try to just abbreviate that. There's a temp. Okay, that is one sign of a chemical change. That's one of the 4. All right, next beaker. What do you see here? You see sometimes people say the word smoke. It's not exactly smoke, but it is a vapor. Okay, to have smoke, you need to have a fire. We don't have a fire here, but we do have some vapor. So is this a chemical or a physical change? Well, I see it kind of looks like ice maybe, or liquid that's boiling or just evaporating really quickly. So this is a physical change. All right, you have liquid, and then the vapor here is gas. So we're going from liquid to gas. That's just a physical change. Okay, the next picture, we have a very colorful substance. It's a powder, it's a solid. So there's actually 2 signs that we could derive here, depending on what starting material we had. Oftentimes in chemistry, you're working with compounds that are white, or they're translucent, they're clear liquids. So if something becomes colorful, that is sign of a chemical change. So we'll say chemical. And one sign is that you have a color change. That lets us know it's a chemical change. Or we could look at this another way. Did we have any liquids to start out with, or gases, and now we have a solid? Well, previously we were talking about that being a physical change, but if you have how do I say this? If you have liquids, okay, we're going to do this in the lab when we first come in to do our face-to-face lab. If you have two liquids, two solutions, and you mix them together and you form something that is solid, kind of imagine a test tube that's clear and then it turns cloudy, and you form something that's solid, you have formed what we call a precipitate, okay? I'm going to write that word out. Okay, a precipitate, you might have heard the word precipitation before, okay? If we're talking about snow, we get excited, that's a form of precipitation, but a precipitate is forming some kind of a solid, all right? And that is evidence of a chemical change because previously you had liquids and now you have formed a solid seemingly out of nowhere. That's a chemical change, okay? So I'm actually gonna move this word over a little bit. So formation of a precipitate is evidence of a chemical change, okay? Lastly, this picture over here, you have some metal shavings. So say you had a hunk of some kind of metal, maybe lead, and you grind it down into smaller bits. Would that be a chemical or a physical change? Are you altering the chemical makeup of that substance? No, we're not. We're just breaking it into smaller pieces, but we still have the same substance. So this would be a physical change. Okay, you probably still have a lot of questions about this, and that's okay. We're going to look at several more examples. Let's continue on. Before we address more specific examples, I want to discuss this phrase right here, states of matter. We have three major states of matter that we're going to discuss here. We're not going to talk about plasma. There is a fourth state of matter called plasma, but we're going to look at solids, liquids, and gases. So let's examine solids really quick. This might seem kind of like some basic information that you know, and that's great. If this is a review, that is great. How do we know when we have a solid? Okay, a solid has, I'm going to underline some words here, has definite volume and definite shape. All right, we see ice cubes here. The best example that we walk through this with is the substance of water. When water is a solid, we know it as ice, definite volume, definite shape. Okay, what about water though? Liquid. When it's liquid, you have a definite volume, but you have a variable shape. That liquid will take on the shape of any container that it's placed in. Okay, so that's how solids and liquids are different. What about gases? A gas has a variable volume and variable shape. Okay, a gas can be compressed into a small beaker, or if you open the lid of that beaker, it would fill a room. Okay, so it can condense or expand depending on the size of its container. So a variable volume and shape. I'm going to draw some pictures on this next slide. That's why I left this slide blank. If I didn't leave it blank for you, you might want to just grab a piece of paper. Let's look at what the molecules are doing in solids, liquids, and gases. So for a solid, at the molecular level, you might see something that looks like this. The molecules are going to be close together. Okay, so all these little spheres could be individual molecules. They're going to be close together, and they're going to be very organized. Okay, and they're not going to be moving a lot, so that's like what a solid might look like. What about a liquid? A liquid, the molecules will be fluid. Okay, it's kind of a word that defines or describes a liquid. So you have the same kind of molecules here, but in a liquid, they're going to be spread further apart. And I'm going to draw some arrows to indicate that they might be moving past one another. Draw another one here. Okay, so they'll be fluid, they'll be moving, and they'll be further apart. So here in a solid, they're close together. And here they are spread apart, and they're moving. Here they are not moving. They might be like vibrating in place, but they're not moving the way they are in a liquid. Okay, what about a gas? What are the molecules doing? In a gas, the molecules are very far apart. So I'm gonna draw them like really far apart. And they're gonna be moving really, really fast. So I'm gonna draw like a double arrow to indicate that they're like flying around really, really fast. Okay, they might be colliding with one another, but they're moving very, very fast. So these are very far apart. The molecules are, and the molecules are moving very fast. Okay, so that will help you with something we're going to get to in a minute. Just kind of keep this in the back of your mind of how the molecules are behaving in these states of matter. So if I say the phrase states of matter, I'm talking about solids, liquids, or gases. And changes between solids, liquids, and gases, between these are all physical. Okay, because you have the same substance in every step. You have water as a solid, water as a liquid, or water as a gas. You did not change the compound of water. To further illustrate this point, I've got two pictures here. The one on the left is a physical change. Let's look at it first. This is still, we're just talking about water. This looks like a coffee pot. In the bottom, you have liquid water. Okay, that kind of corresponds right down here, H2O. You'll notice we often abbreviate the state of matter after we write a compound in any kind of reaction. So this L right here indicates we're talking about liquid water. And then if you look at the top of the coffee pot, you notice some sort of steam or vapor, and this is water in the gas phase. All right, so if you follow the arrow over to this side of the slide for this picture, now we have water as a gas. All right, so this is why we're saying this is a physical change. We're just transferring between two states of matter, but we did not change water. It's H2O in both cases. All right, but if you slide over to the right side of the slide, we said this is a chemical change. So if you notice, you've got some sort of kind of like battery pack here in the back, and then you've got these wires that are connected to some sort of electrode. And what we're doing here is we are running an electric current. We're running electricity through this water. And so we've got this also written down here at the bottom of the slide. We're going to run an electric current through water. What's that going to do? Well, what I notice in these test tubes, you may see are gas bubbles. Okay, we're creating gas bubbles. Well, what is that doing? What our reaction tells us, if you follow the arrow over, is that we're creating hydrogen, and it's a gas. So hydrogen is naturally a gas in its natural state, and then oxygen as well, and its natural state is a gas. So that's what the gas bubbles are. We're creating hydrogen and oxygen. So this is chemical because we no longer have water. Okay, we're breaking water down into its elemental forms of hydrogen and oxygen. All right, again, if you have any questions as I'm going through any of this, or if you think I'm moving too fast, stop me, rewatch anything, write your questions down, email them to me. Last example before we move on is, I like this example with some lighter fluid. Honestly, I hate these kinds of lighters. I prefer the trigger kind because I always burn my thumb on these kinds of lighters, if anybody's with me on that. But, uh-oh, what happened? Oh gosh, right here, okay. We have defined these two pictures, one as a physical change, one as a chemical change. So in keeping with our discussion, let's talk about the physical change first. So lighter fluid, I'm not exactly sure what the molecule is. It may be propane, it may be butane. That's really the common molecule you find in lighter fluid. But what you notice is that we put some molecules in here. Okay, need the pencil. These molecules are composed of some white spheres and some black spheres. Okay, the black would be carbon, and the white would be hydrogen. So we have some. We're going to call it propane. Okay, and you've got black spheres and white. Black is going to be carbon, the white is hydrogen. All right, and all the molecules are identical. Now, at any given time, because this is not necessarily a closed container, the lighter, that is, these propane molecules may evaporate. Okay, down here, this propane is liquid. But if you notice up here, it's still propane because the molecule is identical. It doesn't look any different. If you counted the number of white spheres, it would be the same. So this is still propane, but now it's a gas. Okay, so this is why we're saying it's a physical change. We're just changing between states of matter from liquid to gas. The molecule itself did not change. Over here, if we were to strike the lighter, you would, by evidence, you see the flame happen. We still, down here in the lighter fluid, we have liquid propane. But now we have reacted this propane with, anybody know what you actually are reacting your lighter fluid with when you strike it? It's going to react with oxygen. Well, where did the oxygen come from, you might ask? It's just in the air. It's just present. So when it reacts with oxygen, what is it going to create? Notice that the molecules up here are different. We no longer have propane. Propane looks like this. Well, the molecules up here, where did the red spheres come from? That is the oxygen from the air that you reacted the propane with. So we have two different looking molecules. Notice we have one that is one red sphere and two white. We have another molecule that's two red spheres and one black. So what did we create? Well, anytime you do a combustion reaction, which is what this is, you create two very predictable products. You create water, H2O, and you create carbon dioxide, CO2, right? So this is a chemical change because we took one molecule and we created two new molecules, water and carbon dioxide. So that leads us to this slide. And I want to kind of reassess. We'll do this periodically through lectures. I'll have some sort of poll question on Zoom that I'll launch. But I have just kind of a review here. Based on the molecular diagrams below, classify each change as physical or chemical, so A, B, and C. And actually what I want you to do as you're watching this video, there's going to be a quiz on Blackboard that I want you to complete based on this slide. Okay, it's going to be A, B, and C. So I'm going to create, there'll be a quiz folder and you'll go in there and it'll just say lecture 1 quiz. And I'm actually going to walk through part A with you, so I'll give you the answer here. But essentially, I need to know if people are actually attending the lecture or not. I have to report non-attendance and such. So if you watch this video, you're going to know to take the quiz, and that's going to tell me that you attended and were not just attended, but you were engaged with the lecture. And so let's look at A, B, and C. I'm going to walk through A with you, and then I'm going to skip over B and C because you'll do those on your own on the quiz on Blackboard. So literally, after we do this, pause the video, go do that quiz, and then continue with the video. So A, is this a physical or chemical change? Well, I noticed that in my molecule over here, I have some black, some red, and some white. And all the molecules look identical. They're close together on the left side, and then we go to the other side of the arrow, the right side, they're more spread apart. But I still have one red sphere, a couple of white, and a couple of black. So the molecule looks identical to me, meaning the chemical makeup is the same. It's just that they're more spread apart. So maybe they went from like a solid to a liquid or a liquid to a gas. And this is just a change of state. So this would just be a physical change. So apply that same kind of thinking to parts B and C right here, and just go onto Blackboard. A is physical, and then tell me, is B physical or chemical? Is C physical or chemical? All right, I'm going to continue on. Chemical reactions. So we identified, how many have we identified so far? Signs of a chemical change. I remember I told you there's going to be 4. I know we talked about a temperature change. I know we talked about a color change and formation of precipitate. So that was 3 of the 4 changes. I'm going to continue talking about this water reaction. So we actually looked at this on a slide earlier. If we have water as a reactant, and we were to run electric current through it, creating hydrogen and oxygen, which will be our products, we could do this, but if you're just trying to imagine it, or if you're actually doing it in the lab, what is going to tell you that it's a chemical change and not just a physical change? What's going to be the sign? What can we look for to let us know this is chemical? Well, we mentioned earlier that hydrogen and oxygen in their elemental state, they're both gases, okay? So this is a gas and this is a gas. And water is a liquid over here. So when you go from a liquid to a gas, you should see some sort of gas bubbles forming, which is what we saw in the test tubes, okay? So if we see gas bubbles in any kind of reaction, in a test tube, if we mix things together and we get bubbling, and I mean it's usually pretty profuse gas bubbles, that is a sign of a chemical change. So that's actually our fourth sign. All right, another example, I'll run through this really quickly. If we combine nickel and hydrochloric acid, nickel is going to be a solid and hydrochloric acid will be a liquid. Okay, our products would be nickel 2 chloride and hydrogen as well. And we know hydrogen is going to be a gas. So if we did this chemical reaction, how do we know a chemical change is occurring? Well, if you're paying attention from the first slide, or from the first number 1 up there, you're going to get gas bubbles again. Okay, so that's a sign. But here you have to know a little bit more about chemistry to answer this one. This figure is actually in your textbook, so if you read, then you might already know the answer. Nickel compounds. Now, nickel by itself is not going to be. It's going to be like the metallic, metal silver color. But when it's combined with something else, so here we have nickel combined with chlorine, nickel compounds are green. Okay, so this solution would turn green. So we would get a color change, which we know from earlier is one of the 4 signs of chemical change. So let's just review here. What are all 4 signs now, one after another, signs of a chemical change? Number 1, we said a temperature change. Number 2, if we get gas bubbles, that's a sign of a chemical change. 3, if we have a color change, then we know a chemical change occurred. And 4, if we form a precipitate, so formation of a precipitate. Okay, so I want you to know these 4 signs for the quiz next week, for exam 1. This is one of the major things I want you to get out of this lecture. Okay, we're almost done. A couple slides left. But I'm going to shift gears for just a second. This is going to help us further understand when a chemical change is occurring. We talked about chemical changes alter chemical makeup, but how you really need to understand things about elements and compounds to know when we are altering the chemical makeup of something. So let's talk about elements. I'm going to just read the top statement on the slide. Elements are represented by chemical symbols, okay? So I've included a picture of the periodic table on this slide, and all 118 of them. You don't need to memorize them, don't worry. But I've kind of boxed in several that might seem familiar to you. So like hydrogen, you see over here, sodium, magnesium, calcium, potassium. These are all things we need in our diets. And what do we have over here? Carbon, nitrogen, oxygen, several elements that we interact with very commonly. What you notice on the periodic table is that elements are represented by letters. Some of them, it might be a single letter, like carbon is just represented by a C right here. And then others, like zinc, might have 2 letters to be represented. And if it's just a single letter, you always capitalize it it's represented by 2 letters, the first letter is capitalized, the second one's lowercase. And we call these their chemical symbol. Compounds are different. Okay, compounds are more complex. Compounds, first off, I'll just read this. They're represented by chemical formulas. Okay, we'll talk about that in just a second, but a compound is made up of 2 or more elements. Okay, a compound is made up of 2 or more elements. So, for example, I've got 3 compounds listed over here on the right side of the screen here. Water being the first one, H2O. This is the chemical formula for water. And then we have methane, CH4, and I'll make you guess the last one here in a minute. Water, what elements are involved in water? We've got hydrogen atoms and oxygen atoms, okay? Now, to write out a chemical formula, we have to denote the element. So we're going to write the chemical symbol for the elements, and we have to denote how many of that element. So that's why you notice if we have 2 hydrogen atoms, we write a 2, H2O. And if there's 1 oxygen atom, this is the one exception. There's many exceptions that you'll come across this semester in chemistry. Chemistry is full of exceptions. But when you just have 1 atom, you omit writing the number 1 in the chemical formula. Okay, so you do not write a little 1 down here. That's because you're writing the letter or the chemical symbol itself. You don't need to write a 1 if there's only 1 of that kind of atom. So H2O is the chemical formula for water. Now notice too, the last thing I'll point out is that these numbers, when we're writing in the numbers, we write them as subscripts, okay? Slightly smaller and a little lower than the letters, okay? All right, CH4, this is methane. Okay, so we have 1 carbon atom and 4 hydrogen atoms. So we did not need to write anything after the C. We just write C for that 1 carbon atom. We don't need to write a 1. And then you write H4 for the number of hydrogen atoms. Okay, what about this chemical formula? C12H22O11. So this is a really big molecule or compound. This is actually sucrose. Okay, sucrose, table sugar. Yep, there's 12 carbons, 22 hydrogen atoms, 11 oxygens. So we're going to write carbon, and then we write a 12 hydrogen, and then a 22 oxygen, and then 11. And you might be guessing, how do I know what order to write these in first? I'll probably give you some general information about what order to write things in, or I would list the elements in the order that I want you to write them if I'm going to have you practice writing a chemical formula. But you can see all the numbers are written as subscripts. And that way we know what all is in sucrose. This table, before I move on, I want to mention this table. I really just included this because as you're reading about chemistry or in your textbook, you may come across some names for elements that sound very unfamiliar. And that's because a lot of times different elements, especially transition metals, which I haven't even addressed that, have I? Different metals that are in this block right here. These are transition metals. They can be called by their old Latin name. So for example, this column over here, you see the name in English, and then you see the Latin name in parentheses. I'm not going to be using the Latin names at all, but I at least want you to be familiar in case you run across them and you're like, what in the world is cuprum? That's copper, okay? So just want you to know that does exist. But another thing I wanted to point out about the periodic table, actually I'm going to save that for chapter 2. There's different colors on here, the yellow and the purple and the blue, which denotes things that are solid, metals, and then non-metals and metalloids. But we'll get into that with chapter 2. So let's review. What are the rules for writing chemical symbols and then chemical formulas? Well, for chemical symbols, you have some that are single letter symbols, and these are capital letters. And then if you have a 2-letter symbol, you capitalize the first letter. And then the second letter is lowercase. All right, what about chemical formulas? These are for compounds. And remember, compounds are 2 or more elements. Chemical symbols are just for individual elements. So formulas contain letters and numbers. Okay, it's an N. Letters and numbers, and all numbers are written as subscripts except number 1. We omit number 1. All right, promise we're almost done. Going back to the big concept here, we started out this whole lecture talking about matter. We said chemistry is the study of matter. And you may realize by now there's all different kinds of matter, okay? So one of the other main things I want you to get from this first lecture is how to classify matter. That helps scientists and chemists know what they're studying and better study it when we can classify it. So we're going to walk through this table. For exam 1, I definitely want you to know how to classify things as an element, a compound, or a heterogeneous or homogeneous mixture. So I'm going to turn this sideways. All right, so let's just start at the top. If we have some kind of matter, the first question you might ask is the composition of my matter varied or not varied? Meaning, a better way to phrase that would be, does it just have one thing, or is it made up of more than one thing? If it just has one thing in the matter, then you're dealing with a pure substance, which could either be an element or a compound. But if it has more than one thing, and we'll look at examples, then you're dealing with a mixture. So let's go to the left side and let's talk about the pure substances. If it is a pure substance, then all you have to do is decide if it's an element or a compound. If it's an element, it cannot be separated into anything more simple, okay? So the question we're asking here is, can we separate it into simpler substances? If we cannot, then you have an element. That's as simple as it gets, okay? You can't separate an element. It's just, the example here is helium, okay? So if we have some sort of balloon, helium balloons are the ones that float. They're the good ones, right? All these spheres in this box are green and they're identical, okay? I know some look faded, but it's just trying to give you a 3-dimensional kind of view. So don't think that's a different color here. These are all the same identical spheres. They're all giving you an example of a pure element, helium, okay? If our substance could be separated into something simpler, then you have a compound, like water, okay? We talked about if we run electric current through water, you can separate it into hydrogen and oxygen. We have a glass of water here, though, and we're looking at an example of a compound in molecular form. Then you see everything in this box is identical. You have 2 different kinds of elements, so the white would be your hydrogen, and then the red, I'll just point to this one. The red would be your oxygen. So you have 2 different kinds of elements, but all the molecules, all the water molecules, look identical. 1 red and 2 white spheres. All right, so that's pure substances, elements, and compound. Let's go back to the top. If your matter is made up of more than one thing, many things, you're dealing with a mixture. And we have 2 kinds of mixtures. All right. If we have a mixture, the next question to ask is my mixture uniform throughout? Okay, if it is, then you have what's called a homogeneous mixture. The example they give you here would be like sweet tea. Okay, if we dissolve these sugar cubes into the tea, that sugar is going to be evenly dispersed once we mix it, right? So that's what the picture down here shows you. These big bluish looking molecules might be your sugar molecules, but then you also have water molecules, so you have many things going on here. And that's why it's a mixture, but the sugar should be spread throughout. Every sip of your tea should taste the same. My favorite example would be vanilla ice cream, Okay, think about what all's involved in vanilla ice cream. You've got ice is in ice cream, so water is in ice cream. You've got air mixed into ice cream, believe it or not. You've got milk in ice cream, and milk has a lot of things. Milk has proteins in it, milk has sugars in it, milk has fats in it. Milk is like a huge percent water, actually. So you've got all of these different things mixed into vanilla ice cream, but every bite of good vanilla ice cream should taste the same, right? So that would be considered a homogeneous mixture. So I'll actually write that here, vanilla. Okay, or chocolate, any kind of, pure flavored ice cream. Now, if the mixture is not uniform throughout, then what you have is called a heterogeneous mixture. The example it gives you here is kind of a sandy beach. If you were to scoop up some of that sand water mixture, it might look like this square here. Okay, so you have like all the sand portion down here, and then you have water molecules on top, but it's all mixed together. Wet sand here, and it's just heterogeneous. It's not even throughout. You might have water on, you have different layers in a heterogeneous mixture, but they're all kind of mixed together. My favorite example of a heterogeneous mixture would be like cookies and cream ice cream. So I'm going to write that here. Okay, cookies and cream. The moment you crunch up some Oreos, put it into your vanilla ice cream and mix it up, not every single bite is going to be the same. In one bite, you might get a big piece of Oreo. In another bite, you might have more ice cream. So that would be an example of a heterogeneous mixture. All right, so that's how to classify element, compound, and then your two kinds of mixtures. So this is kind of a recap. That's all the lecture material for today. What are the major things we got? I like to do these when I remember to and as I can. Number one, we looked at matter and what chemistry is the study of matter, but we looked at physical and chemical changes. And how to identify between the two. And then a subset to that, we identified the 4 signs of a chemical change. And I've already written those out, so I'm not going to do that here. 2, we looked at elements and compounds. And how to identify our chemical symbols versus chemical formulas, how to write chemical formulas. And then 3, we looked at how to classify matter into an element, a compound, or a heterogeneous or homogeneous mixture. So that's what we covered in the first lecture. Hope you guys hung with that okay. Last thing I wanted to mention is I want you to get a head start on knowing some polyatomic ions. Okay, this is actually chapter 3 stuff, but it is really going to help you out in this course if you will take the time to memorize. And I know you're thinking, why would I take the time to memorize anything? All the exams are open note, open book. Well, I promise you, you're still going to have limited amount of time on exams. So memorizing some of these polyatomics early on is really going to help you. Here's the ones I want you to take the time to memorize. A polyatomic ion, you're probably like, I have no idea what this even is, and that's okay. I just want you to know the ones that I box in. I want you to memorize the formula and the name associated with that formula, okay? So these right here, these first 5, hydronium, ammonium, acetate, carbonate, and the hydrogen carbonate ion, I call it bicarb. And then the hydroxide ion, OH minus, nitrate and nitrite ions, and phosphate, and 2 more, sulfate and sulfite. If you will know, I think there's 11 here. If you will know these 11 polyatomics, it will really help you moving forward with this chemistry course. So that concludes our first lecture. Stop sharing my screen for a minute. Hope you guys enjoy that, and I'll see you on Thursday.